5 of normal distribution. So we've learned how to use normal CDF on the calculator, and we've learned about standard normal distribution. Now we're going to take a look at how to use the inverse norm. Remember that up until now, most of our problems had to do with taking two or one value on the x-axis of the normal distribution and figuring out what is the percentage chance that the random variable falls within those two intervals, and we get a percentage or a decimal out, right? Now we're going to do the opposite. What we're going to do here is we're going to have a area, a percentage, and then we're going to figure out what value that would be so that it corresponds to that percentage, given a certain mean and standard deviation. It turns out that depending on what calculator you have, it is different, and the old TI-84 works a certain way, and the CE works a certain way, and the CE is definitely easier to use, but I'm going to show you how to use the old TI-84 here, and then I'll also talk about how you would do it on the CE, which is much easier. Okay, so number one, suppose that Z is the standard normal distribution. So remember, that means that the mu value is 0 and the sigma value is 1. Illustrate with the sketch and find K such that the random variable Z is less than K and the probability is equal to 0.81. So I'm going to say that, okay, maybe it's like this. So like 0.81 would be like a really big probability, and I'm going to say it's below this K. And yeah, that's right. The probability that the Z variable is below this K, I drew it correctly, right? And then I'm going to figure out what this K value is, assuming that the mean value is 0 and the standard deviation values are -1 and 1, right? So how do we do that with the calculator? We're going to use this procedure here. We're going to do second distribution, and then second distribution, and we're going to go to inverse norm, and then we're going to put that the area is 0.81, and since we're doing standard normal distribution, we just leave mu and sigma as 0 and 1, and we hit enter twice, and we get 0.878. So K is equal to 0.878. All right, so that looks like it's about right? This looks like it's about a K equals 1 or so. So 0.878 seems like a reasonable value. Next one, probability that Z is less than K is 0.58. So that would be about a little more than half of the area. And Z is less than K, so the shading would be to the left, right? So let's find this value of K. Let's see, so I'm going to go back to second distribution inverse norm, and then I'm going to type 0.58 and just leave 0 and 1 and hit enter twice. 0.202. So K is equal to 0.202. Now, how would you do these two problems using inverse norm on the CE? For the CE, it turns out it can do any kind of area, whether that area be to the left or be to the right, and it's kind of like the equal ease. So like whether or not you're going to do it on the left or the right, you're going to put in the area of the shaded area. So like in this particular case, for example, the shaded area is 0.81, so we type in 0.81 for the area, 0 and 1 for mu and sigma, just like in the old T84. But look at the end, it asks you where the tail should be. And in both of these cases, the tail would be left, because see how the shading goes to the left? So on the new CE, we would just put left, and then we would hit paste, and it would do the exact same thing as the old TI-84. And you're saying, I don't see what's easier about this. So you'll see why it's easier when we go down to problem 3, but let's finish up problem 1 for now, okay? So problem 1 is similar to the first two that we did, except the area is much smaller, right? 0.17. 0.17 is much smaller than 1/2. So if I was to do a left shaded area with 0.17, it would be kind of like that, right? So let's use inverse norm to figure out what the k value would be here in the standard normal distribution. So we do second distribution, inverse norm, and then we put 0.17, and then 0 and 1, and then we hit enter twice. Negative 0.954. Negative 0.954. Negative 0.954, does that make sense? Yeah, I guess so. Because remember, a k value on the left side of a mean of 0 should be a negative value, right? So, okay, yeah, that makes sense. All right, let's go down to number 3. In number 3, we're going to do our first right shaded area, but the first one is left shaded. So let's do number 3. Oh, number 3 is a little bit difficult because look, instead of just giving us mean and standard deviation, they give it to us in the the normal distribution notation, which basically says that the first value in the parentheses is the mean, and the second value is sigma squared. So here we can see that the mean here is 38.7, and the sigma is equal to 8.2 because the sigma squared is 8.2 squared, right? So let's write that down on our picture. So 38.7 is the mean value, and 8.2 is the standard deviation. So the standard deviation would be 8.2. Okay, and then we'll find out what is the k value if the probability less than k is 0.9. So wouldn't that be like almost the whole thing here? So this is our k value right there. We can, using inverse norm, of course, just like we did before. We're still doing a left-sided distribution, so we do second distribution, and then we do inverse norm, and we're going to type in 0.9 for our area, right? 0.9. And then instead of 0, 1, we're going to put 38.7 and 8.2 because that is our mean and standard deviation. And then we paste twice. Paste or hit enter twice. And the answer is 49.2. Does that make sense? Yeah, k looks like it should be about 49.2. Slightly to the left of 38.7. It's about 10 units to the left. That looks like it's about right. Okay, last one. Now notice that this one is a right-sided interval. Okay, now on the CE, all you need to do is put 0.8, just like you did before. Except now you're going to put the right-sided interval, like a right-shaded interval. Let's draw the right-shaded interval. So if it's 80% probability that it's bigger than k, then we're going to have k on the left side, and then we're going to have a big region more than half to the right, right? So this is a right-sided region, and in this case, again, we have the mean of 38.7, and we have a standard deviation of 8.2. Let's use inverse norm to calculate this on the old calculator. Now, the old calculator always assumes that the area you're giving it is actually a left-sided area. So if it's always assuming it's a left-sided area, how can we give it a right-sided area? Well, remember, this right-sided area is 0.8, right? What we do to trick the calculator is we give it the white area. The white area is actually going to be 1 minus 0.8, which is actually equal to 0.2. So if we give the calculator 0.2 instead, it'll give us the correct answer. So we'll say, okay, the white area, which is a left area, is 0.2, and the mean and standard deviation are the same as before. What is the answer? 31.8. So this k value is 31.8. Okay, so that's how you trick the old calculator into giving you the correct answer. Now, how do you do it on the new calculator? You just put 0.8 instead of 0.2. You just put the regular area of 0.8, and then you click on right, and that'll give you the correct area. Okay, we never use center in our class, so you don't need to use that. All right, the students of class X sat a physics test. The average score was 46 with a standard deviation of 25. The teacher decided to award an A to the top 7% of the students in the class. Assume that the scores were normally distributed. Find the lowest score that would achieve an A. Okay, so the mean is 46 and the standard deviation is 25. So 25 plus 46 would be about 71. 25 subtracted from 46 would be about 21. And then top 7% of the students, that would be a very small area, about like that. So the teacher decided to award an A to the top 7%. Let's find the minimum score necessary, which would be this K value here, okay? So this area is 7%, also known as 0.07, right? So let's do second distribution. We're going to use inverse norm. And remember, with the old calculator, we need to give it the right side area. And the right side area is the white area. And the white area can be calculated by subtracting 1 minus 0.07, which will be 0.93. So the white left area is 0.93. That's what we're going to feed the old calculator. If it was the new calculator, we could just do 0.07 and specify that it's a right side area. Of course, the mean is now 46 and the standard deviation is 25. And then we hit paste and enter, and the answer is 82.9. So the K value here is 82.9. That is the lowest score that would achieve an A. All right, number 7. The length of a screw produced by a machine is normally distributed with a mean of 75 and a standard deviation of 0.1. 75 in the middle, 75.1 to the right, and 74.9 to the left. If 1% of the screws are, or if a screw is too long, it is automatically rejected. So the screws that are too long would be over here on the right side, right? So this is a right side area. If 1% of the screws are rejected, what is the length of the smallest screw to be rejected? So this, of course, is area 0.01, and this would be the smallest screw to be rejected, which would be length K. And since this is a right side area, if it was the CE calculator, we would type in 0.01 and say that it's a right side area. We would click right here. Since we're using the old calculator here, what we're going to do is we're going to do second distribution, inverse norm, and we're going to put the left side area, the corresponding left side area, which is 1 minus 0.01, which is 0.99. So I put 0.99 in for the area, 75 and 0.1 for the mean and the standard deviation, and I get 75.2 for the K value. All right, last problem, number 9. The volume of cool drink in a bottle filled by a machine is normally distributed with a mean of 503 and a standard deviation of 0.5 milliliters. 1% of the bottles are rejected because they're underfilled. So that would be the bottles down here, 1%. And 2% are rejected because they are overfilled, 0.02. Otherwise, they're kept for retail. What range of volumes is in the bottles that are kept? Okay, so the shaded regions here are the rejected bottles, and of the white region in the middle, of course, are the bottles that are kept. So let's figure out what these two values are. Let's say that this value is M and this value is N. So let's figure out what the values are for M and N using inverse norm. So of course, first of all, 0.01 on the left side is a left interval, and the old calculator is really good at doing that, right? You don't need to do anything special. You just put 0.01, which is the left area. We say that the mean is 502. Actually, it's not 502, it's 503, right? 503, and the area is 0.01, and the standard deviation is 0.5. So the answer is 501.8. So the M value is 501.8. Okay, so that would kind of be the edge of the white region and the dark region there. let's figure out what the value is for n, which is the right edge of the white region. So we're going to again do second distribution, inverse norm. Now this one is tricky because it's a right-sided region. The right-sided region, remember, the old calculator can't handle that. We need to figure out what is the complementary region to the left. And so if the right side region is 0.02, the left side region would be 1 minus 0.02, which would be 0.98. So if we put 98 in the calculator, the old calculator is capable of finding the right k value. And so the mean is the 503 and the sigma is 0.5. And the answer is 504.0. So the n value is 504 in that case. Okay, so they're asking what is the range of volumes of the bottles in the white region that are kept. So that would be 502 to 504. And that's it.